Hi everyone, welcome to Church of Logic. I'm your host Cody Rue, and today we're going to talk more about the completeness theorem. So last time we mentioned soundness, where if something is provable, then it also holds in every model of your axioms, right? Every model that makes every axiom in your system true will also satisfy all the provable statements. This is the least we can ask of a formal system, kind of that it makes sense in your intended semantics. Completeness is the converse of that statement. It says that any statement that is true in any model of your axioms happens to also be provable in your syntactic system. Now, this is much less obvious, and in fact, it doesn't always hold. There are many formal systems with kind of natural semantics where there are things that are true in every model, but that still can't be proven by your axiomatic semantics. Okay, but in first order logic, classical first order logic, this holds. It was proven early 20th century by Kurt Gödel, and it's a very powerful theorem that has a lot of cool consequences. So I'm going to talk today a little bit about what the statement says in more detail and possibly how one might go around proving it. So, like I said, the completeness statement basically takes a set of axioms and a given logical formula, and it says, okay, well, if all the models of that set of axioms validates that formula, right? So if that formula is true, then actually you can go back to the syntax, and the syntax is strong enough to be able to prove that thing. All right. One way to state this, which will be useful later because it's going to enable us to find a proof strategy, is that if a set of axioms has no models at all, well then it is provable from that set of axioms to prove the false statement, to prove false. All right? So this is kind of a cool way of restating it, right? If you can prove false, if you can prove an absurdity, right, that's a very strong constructive statement about your set of axioms. But this is actually the same thing, because saying that a theory, a set of axioms has no models is really, if you unpack the definitions, the same as saying false is true in every model, right? If there were a model and false were true in it, you'd get a contradiction. And so that can't happen. And so you have no models, right? So saying false is true in every model is the same as saying a theory has no models. And the completeness says, the completeness theorem says, if something is true in every model, in this case false, then this thing is provable from the axioms of the theory. And so false is provable. All right, great. So if we just take the contrapositive of this statement, right, then basically, if the conclusion of the statement is false, then the premise is true. All right. And what is the contrapositive, right? It says if a theory can't derive a contradiction, if it can't derive false, then the set of axioms has at least one model, all right? It has some models, all right? And this is actually the thing we're going to prove. What's kind of cool here is that the proof just does not make any assumptions about whether the set of axioms is finite or not. In particular, we're going to be able to prove this theorem for any arbitrary infinite set of axioms. And that's going to be really cool because it's going to imply this really powerful corollary to the completeness theorem called the compactness theorem. All right. So what we're going to prove now is this last statement, which is if a theory T does not prove false, which we often say as a theory T is consistent, then it has at least one model. Now, this is a little bit daunting to prove because basically the form of the theorem is if something can't happen, which is T can't prove, a contradiction, then something constructive happens, right? Something positive happens, which is, you can find a model, you can construct a model, right? And this is often a daunting task in mathematics because you're sort of saying, okay, here's something that doesn't happen. Now show that something actually does happen, right? And you have nowhere to start, right? If you had something does happen, therefore something else happens, you'd have kind of a plan of attack, which is take that first thing and see if you can't use it to build the second thing. But here, all we have is, you can't prove false. Okay, and somehow we have to hatch a model out of this assumption. Okay, but logicians are very clever people, and they've managed to prove this theorem. And the strategy here is typically to find a model that kind of looks enough like the syntax. And then we're going to use the fact that T doesn't prove false to show that this syntactic model you're building actually can be turned into a bona fide model. All right. These syntactic models are often called Herbrand models. And a Herbrand model is basically you take all the syntax of your theory. So you take all your function symbols and your constants, and you say, okay, well, the set of individuals, the set of things we talk about in the logic are just going to be all those syntactic entities. Now, that's not quite enough because you could have an axiom in your theory that says there exists X such that some property, right? And you might not have a piece of syntax that denotes that X. So there's this step that I'm going to kind of gloss over where you sort of say, okay, well, I'm going to add all these X's that exist via, existential statements. And there's a very kind of clean way to do that, which is sort of eliminate all existential statements, add a bunch of atoms or constants to that. And that was Herbrand's big idea, I believe. And okay, so now you have the individuals. Now you need interpretations for the relation symbols. And, well, how do you do that? Well, you just take you take the relation symbol to be defined as all the things that are actually provable from your theory. And here's where we kind of use our assumption that the theory is non-contradictory. So if the theory is non-contradictory, then, a relation symbol is, an atomic relation symbol, R of XYZ, for example, might be provable for some constants, or the negation might be provable, or neither, right? But certainly not both. You can't prove a thing and its negation because the theory is consistent. All right, so you take whichever one it can prove, and you just add it to the interpretation, right? If R of A is provable, then you add A to the domain of definition of the relation R. And if not R of A is provable, then you exclude it, right? You know it won't be both. Now, it could happen that neither is provable, right? Neither R of A nor not R of A is provable. And then you don't really know whether to add it or not in the domain. Now you could say, well, let's just not add any of those, but that's not quite good enough, because if you say R of A is false for all atoms A such that, R of A is not provable, then you might get into some awkward situations, right? If you have an A and a B and you have R of A if and only if not R of B, then you have to add one of those two and exclude the other, right? So you can't exclude both. You have to have R of A holds and R of B doesn't hold, or vice versa, right? So you have to make these kinds of choices. So the solution here is to kind of just make an arbitrary choice. And when people use the words arbitrary choice in a mathematical proof, usually it means they're using the axiom of choice. And in this case, indeed, you really do need the axiom of choice in some form, in some weak form. And basically it tells you, you can make kind of these consistent guesses for whether R of A is going to be added in your model or not. And you sort of make a bunch of random but consistent choices. And there's a lemma called Zorn's lemma, which says exactly, in which cases you can make arbitrary but consistent choices and end up with kind of a maximal a maximal choice where you've basically either added A in your domain or you've excluded it, but you've done one of those two. And then you're done, right? You have a model. You know what the domain of your relations are. You know what your syntax is. You're done. You have a model. You've used the fact that the theory is non-contradictory. You haven't used the fact that the theory is finite. This works for any infinite theory. And you have a proof of completeness. You know that all of the statements that are true in every model are actually provable. Okay, next time we'll talk about a really powerful consequence of this, which is the compactness theorem, which basically is a way of saying, hey, if I can build models for every finite subset of a theory, right? If I take my axioms and I look at a finite number of them at a time, and I can build a model there, there's a way to glue them all together to build a model for the whole infinite theory. And this turns out to have some delightful consequences, including a very easy definition of non-standard analysis, infinitesimals. All right, so that's going to be exciting. See y'all next time.